Today we're going to talk about one of the most important breakthroughs in the history of AI, a truly revolutionary architecture called ResNet. Now, it solved a problem that was holding back the entire field of deep learning, and it did it with an idea so simple and so elegant it's kind of mind-blowing.
So here's the plan. First, we'll dig into the paradox that had researchers scratching their heads. Then, we'll uncover ResNet's incredibly clever solution, we'll actually build a small version of it, and I'll show you the single line of code that makes the whole thing work. After that, we'll see the results, and then we'll talk about why this idea really did change everything. Let's jump in.
All right, so our story kicks off with a really frustrating problem, a genuine paradox that was at the very heart of deep learning for years.
You'd think it would be simple, right? It's called deep learning because of the number of layers in a network. So more layers should mean it's more powerful, better at learning complex stuff. But what researchers found was the exact opposite. Once you got past a certain point, stacking on more layers actually made the network's accuracy go down. The models weren't just getting stuck, they were literally getting worse. So what on earth was going on?
Well, the main culprit, the big villain in our story, is something called the vanishing gradient problem. The best way to think about it is like a game of telephone. The last layer in the network figures out how wrong it was and tries to shout a correction all the way back to the first layer. But in a really deep network, that message gets quieter and quieter as it passes through each layer, until by the time it reaches the beginning, it's barely a whisper. The early layers get almost no useful signal, so they just stop learning.
So how do you fix a massive communication breakdown inside a 100-layer network? As it turns out, you don't fix the road, you build an express highway. And this is where ResNet enters the picture with its brilliantly simple shortcut. In 2015, this game-changing paper dropped, introducing the world to the Residual Network, or ResNet for short. And it didn't just nudge performance by a few percentage points, it completely smashed through that depth barrier. Suddenly, we could stably train networks with 50, 100, even more than 150 layers. It was a whole new ballgame.
The secret sauce to ResNet is this small but mighty component called a residual block. And the key idea, the whole magic trick, is right there in the definition. It adds the original input to the output. This simple act of addition creates a special path, a shortcut for the information to travel on.
So let's trace the data flow. The input comes in and goes through a couple of standard layers, just like normal. But at the same time, a perfect untouched copy of the original input gets to take this special detour, what we call a skip connection, that goes around those layers. Then, at the very end, that original input is simply added back to whatever came out of the processing layers. This is what creates that uninterrupted information highway we're talking about.
And this right here illustrates the difference perfectly. The standard network has to learn a complete, complex transformation from scratch. But a residual network only has to learn the difference, the residual, between the input and what you want the output to be. By adding the input back, it makes it super easy for the network to do nothing at all if that's the best option. It can just pass the information straight through, which is the key to solving that degradation problem.
Okay, theory is great and all, but let's make this concrete. We're going to map out a blueprint for a smaller ResNet, one that's adapted for a classic, hands-on machine learning problem.
So our job is to classify these little 28 by 28 pixel grayscale images from the Fashion-MNIST dataset. You know, t-shirts, boots, bags, that sort of thing. Now, we don't need a massive 152-layer ResNet for this. That'd be like using a sledgehammer to crack a nut. So instead, we'll use a much smaller architecture that's inspired by the famous ResNet 18.
And here is that blueprint. The image starts its journey at the top, and it flows down. First, it hits an initial convolutional layer. Then it moves through 3 different stages of those residual blocks we just talked about. As it goes, the network learns more and more complex features, while the image itself gets smaller but deeper in terms of information. Finally, a layer called global average pooling neatly summarizes everything the network has learned and feeds it to the final layer, which makes the call. Is it a t-shirt, a boot, or a coat?
All right, let's go from the drawing board to the actual code and see how this elegant idea actually comes to life, because this is where you can really see the heart of the entire innovation. You might imagine that an idea this revolutionary would take hundreds of lines of really complex, difficult to understand code. But the absolute beauty of ResNet is that its core concept, that amazing skip connection, is just astonishingly simple to write.
And there it is. Out equals identity. That's the magic. Identity is holding that original, untouched input that took the shortcut, and out is the result from the main path. This single line of code, this 1+ sign, performs the addition that we saw in the diagram. It is the information highway that lets the gradients flow freely and unlocks the incredible power of super deep networks.
So we have our theory, we have our architecture, and we have our code. The only thing left to do is to fire it up, train the model, and see if our little ResNet can actually learn to tell the difference between fashion items. We put our model through its paces, training it for 100 full cycles, or epochs, on the Fashion-MNIST dataset. And the whole time, we kept a close eye on its accuracy, not just on the data it was training on, but on a separate validation set that it had never seen before. This is super important to make sure it's actually learning patterns, not just memorizing the answers.
And the results were just excellent. The fact that the accuracy is high on both the training data and the validation data is a fantastic sign. It tells us the model didn't just cram for the test. It actually learned the material and could apply that knowledge to new, unseen examples. And that is exactly what you want.
And the final result on the test set? A rock-solid 92.53% accuracy. That's the proof right there. Even a small-scale version of this architecture is incredibly powerful and effective.
So it clearly works. But the impact of ResNet goes so much further than just getting a high score on one dataset. It fundamentally changed how we even think about building neural networks. Let's take a quick look at its lasting legacy. At the end of the day, ResNet gave us a reliable toolkit for building truly deep networks. Those residual connections were the star of the show, obviously. They solved the vanishing gradient problem and let us build networks of a depth that was just unimaginable before. You combine that with other clever techniques like batch normalization and global average pooling, and you get a scalable, efficient blueprint that has influenced pretty much every major deep learning model that has come since. You know, ResNet's biggest lesson was that sometimes the most profound solutions are actually the simplest ones. It wasn't about adding more complexity, it was about adding a simple shortcut. It really makes you wonder, what's the next brilliantly simple idea that's out there, hiding in plain sight, just waiting to unlock the next level for AI?